Mike Feinstein is a exploration geologist, a metals exploration with quite a lot of experience and several ongoing drilling projects to his credit, and hopefully several discoveries pretty soon out of that. And he's going to talk about the tectonics of southwestern North America and its implications for metals exploration. Go for it, Mike.
Wonderful, great. Thank you for that introduction, John. Thank you all for joining us this evening. I'm here in Las Vegas at the regional section GSA meeting for the Rocky Mountain Cordillera, and we've got the AIPG booth set up, and we're representing here for all of the young geos because we need more CPGs in the ranks. So today I want to give you guys a talk that's going to cover kind of the history of North America, and then I'm really going to focus on Southwest North America because we're going over such a broad topic, and to delve all the way to the end, or to delve into just any one little section of North America could certainly take us far more than this hour or so that's allotted. Anyway, just to kind of give you a basic map of Southwest US, showing Arizona there in the Southwest. We've got the outlines of the states. We can see the Precambrian exposures in orange, and that is the keys that we are certainly using to talk about the Proterozoic. That would be Precambrian rocks, right? And we're going to start off diving into that. And then I will take us all the way through current and all of the extension that's later occurred just briefly as well. But that's why we can see that's why we have all this Precambrian exposure to work with, especially here in Arizona and Southern California in this hyper extended corridor. It's an entirely different kind of structural reason that we've got the exposure there in Colorado as opposed to, that massive extension. But that is another topic for another talk. And then we're going to zoom in and we'll talk about maybe some of the reasons this is important, the tectonic environment that your host rocks were sitting in when they were in place, because we've got some very significant ore bodies that have later in place upon those host rocks. And we know host rocks can certainly have variable capacities of importance to an economic geologist, or to a copper deposit or a gold deposit, or an oil and gas deposit for that matter. The host rocks can be far more important than others sometimes. Anyway, diving right in, let's talk about what North America looked like about as long as ago as we can really track, and especially as far away as we can, as far back as we can see in southwestern North America. And I want to point your attention to this little block of Mojave. And so all of these gray cratonic blocks are the kind of roots and pre-cratons of Laurentia, and the Laurentian shield. And so the Wyoming province, there's rocks going back all the way to 3.6 to 2.1 billion years. And some of these other provinces going back to, comparable ages. And we were having collision into the Paleo-Laurentia was coming. And when I talk about directions for purposes of this talk, everything is oriented north. And so if I say it's coming in from the west, you know what I mean. And obviously our paleo orientations are different than just north-south. And so I certainly want to put that little bit of disclaimer out there. So we were having collision into Laurentia from the west, and we were accreting all of these kind of juvenile terrains, these Archean oceanics type rocks. Then we had the Trans-Hudson origin we can see here in pink, and this was kind of the granitic plating of the crust, the orogenic event that was coming through, and kind of sealing Laurentia into a true craton and continent. All right. So, and then I guess we also certainly want to note that here at 1.7 billion years. So at 1.7 years, we've already kind of piled together all of these these gray blocks into the heart of Laurentia. We've still got this little block of Mojave. And as we continue having subduction and accretion, kind of melange accretion, and then compaction coming in from the west, we are going to kind of push Mojave up closer. And that's what we just did in the kind of previous reconstruction. We kind of brought this Grouse Creek block into the Wyoming province. And, you know, we can only kind of recreate so much because we've only got so much rock to work with, and so much of this crust has been reworked and not exposed as well, reworked, and it's not in the right place for us to get an appropriate sample to know what's going on there. Of importance is these green little island arcs that are down here in the southeast of Laurentia. And these island arcs are going to become what we know as the Yavapai terrain in Arizona. And that is an accreted island arc province that was eventually, or as we had accretion and subduction of this island arc, then we had the related magmatism. And then we have continuing kind of accretion onto, well, I guess, subduction and associated accretion onto Laurentia of the Manzano group. But as opposed to an island arc sequence, the Manzano group is ocean sediment layers and oceanic crust. And so we've got a different subterrane coming in. And then as we have additional collision, there's the underplating and kind of accretion of that crust, and then some of the associated magmatism going along with it. All right, and so in that Mazadzal orogeny, we have a slab rollback event, which is then going to kind of culminate in a large granitic rhyolitic province of 1.5 to 1.3 billion years in age. And then in this next figure, we're going to see the prevalence of this granite. And so as we go back, we have this rhyolite province, this juvenile crust, and then we see the massive granitic batholith and rhyolites that have come through and kind of overprinted everything on the inboard side of the plate from this accretion. And so then this green right here would be our Grenvillian crust, all right? And it's the beginning of this continent to continent collision. And then the Llano and true Grenville, and, you know, maybe my names are a little bit off. The Llano and Grenville, that would be the true kind of granitic continent building magmatism from a continent on continent collision. And so this is where we create rhodinia. And then we continue in placing granitoids of that same nature. And then as we get into about 1.9 million years, we start developing numerous kind of intercrustal rifts. And then at about 7 or 0.7 billion years, that's when rhodinia starts breaking up. And we develop the breakup over here to the east. All of these are intercratonic rifts. And so breakup started at about 250 million years ago, separating over to the Southeast Africa and Eurasia, moving back away, and then culminated about 150 million years later, about 600 million years ago. We had full breakup. And we certainly, there are implications that there was two incipient triple junctions, which kind of combined to create a new spreading ridge, which would be the Atlantic ridge. And so that is going to take us just about to the end of the Precambrian. And so we're going to jump through to a different recreation. And I guess excuse me for my negligence as a scientist for not giving credit at the very beginning. All of these reconstructions of the Proterozoic were from the Switmeyer and Karlstrom publication of very important significance in 2007. And you know, all of these different data points are based upon a culmination of many, many studies. And I think it's just so fortunate that we have, or that we're building a good scientific database, and all of this knowledge from generations of work can be integrated and built into these grand these really grand and large scale interpretations and the applications of these little pieces of science here and there. All of this postage stamp work, as I call it, because it's not a state that you're looking at. It's just a section. It's just one township range. Anyway, all of this postage stamp work that we do, it's wonderful to see it culminate in something like this. And so I applaud those gentlemen. And so moving forward, I'm going to jump into the work of Dr. Ron Blakey he had been out of the University of Northern Arizona, or Northern Arizona University, excuse me, maybe I said it backwards. But we're going to go from the Precambrian into present. And we're certainly going to be continuing to focus on North America. And I'm going to give you the southern border just so we've got some context. And we'll also draw on some states. And when we jump forward a little bit, we'll stop looking at all of the Canadian shield as well. And so now we see the North American craton, and we have the breakup of Rodinia in full effect. And we start having sea level rise. We're in the Ordovician. A lot of the continent is underwater. We're kind of going back and forth in these sea level change environments. And we've also probably got some other factors going in, but we're certainly going to see a lot of intercratonic seaways, and the continent is going to be submerged for significant periods of time. But I guess what I really want to focus on is all of this. So we just had breakup and separation to the east, southeast of Laurentia, but now we are going to have 400 million, well, I guess 370 or 380 million years of accretion onto the western side of North America. And we're bringing these island arcs on. And island arcs are really important for minerals because oceanic crust is, 10 times enriched in heavy metals compared to granitic crust. Just the amount of copper, lead, zinc that are inherently in that basalt versus a rhyolite or a granite, the diabase basalt versus a rhyolite or a granite. And maybe I didn't say diabase right. Anyway, sometimes the details, we have to get past them. Anyway, when we accrete all these island arcs, we are slamming and accumulating metallically enriched crust onto the continent. And then as we continue that process of accretion and subduction, we are magnetizing and volatilizing those oceanic and intermediate, the mafic and intermediate rocks of the island arcs. And we've got a lot of mobile metals to work with. And so anyway, as an explorationist, when I see these island arcs slapping onto the side of western side of North America for 400 million years, I get pretty excited. And so we're going to start with it. And I guess I also want to point out that Mexico doesn't exist, right? We've got maybe this tiny little Caborca block, which is a remnant of some Grenvillian crust. And aside from that, it's all gone. And so we're going to start stepping forward. We also don't have California for that matter. We slap that one island arc in there, and then maybe we get kind of distracted by the continental seaway. But we've got our basins, the Anadarko Basin developing, and then also we've got the Midland Basin in full effect in the Anadarko Basin over here. And so we've got these carboniferous basins that are so important to us economically nowadays. But we've still got this kind of western cordillera that's developing, and we can see the cordilleran front right here just on the margin of the continent. And so stepping forward 300 million years, we've obviously got a different situation. I believe this is the Appalachian orogeny. So Rodinia opened and then it slammed back together, and then it's going to rift back open here shortly. But we continue subducting oceanic crust along the western side of North America, and we have some more island arcs that are coming on. I guess another thing of importance to point out is the Paleo-Pacific plate. We see here it coming in, and it's going to get cut. And so we've got this north section and this bottom section. And as this plate is subducted and this new Pacific plate comes in, we're going to have a different angle of attack on the North American craton. And also right here in this Jurassic time, when we have this plate convergence, kind of the directions are going to just start changing, and that's when we have this Sonora Mojave megashear that slices off the western side of North America and tears right down here, coincidentally, just immediately south of the border. It's kind of wild how those coincidences are sometimes. Anyway, we're going to step forward, and we've continued, and so now we have accretion as opposed to coming directly from the west. We're bringing in these island arcs from the west southwest, and so the effect, and so we have this paleo block of Tectonic crust in Mexico that's now developing from the Jurassic Mojave megashear that got brought down, and we're going to start just accumulating island arcs. And we're also, bringing island arcs right here to Oregon and Washington and British Columbia and Alaska as well. That's the same kind of crust, but it's just under a very kind of different tectonic regime than it ends up being down here. So stepping forward, this is the late Cretaceous. This is kind of right before the Laramide orogeny, as we call it, or the Laramide cordillera, which is kind of analogous to that the Andean cordillera that we've got right now, where it's a well-developed subduction margin, and we have inbound magnetism related to the angle of subduction along that plate, and so we are developing that along the western front of North America, and we develop it quite well. And you can see here at 75 million years, which is just right in the heart of the Laramide, or I guess the early heart. We call the Laramide about 80 to 60 million years, and that would be the timing of the Laramide aged plutonic rocks. And then a lot of times we want to say Laramide porphyry coppers in Arizona, and that's kind of an age determination as to which metallogenic period all those porphyry coppers came in. And it's right here. And so, we can see the development of this cordillera, and it runs all the way down Mexico and all the way up to BC and even into Alaska. And the exploration for these porphyry systems and the related mineral deposits that come with them has seen a real exploration boom in the last few years. And I guess maybe one of the things to point out about all of this incredibly prolific magnetism and mineralization is that these porphyry copper deposits and then the related epithermal veining and intermediate sulfidation veining that's coming in above them are placed at the top of mountain chains, and that is the first thing that erodes. And so a lot of the upper portions of these systems are not preserved, but certainly you can have that in sometimes. You can have that sometimes, but at the same time, that's also a big reason why our historic maps maybe, or when we were talking about that Precambrian and we were looking at some of those batholithic granitoid events that were following magmatic arcs, I think that maybe part of the arc was incised to the point where, yes, it was just those batholithic rocks versus the kind of eruptive components, and so we cannot see them in the rock record the same way. Anyway, maybe that's just a tangent that I need to pop back off of. Here at 65 million years ago, we've got this continued subduction along the western front of North America, and continuing forward. And so we are just subducting crust. We've got a well-developed cordillera. In Mexico, this is represented by the Sierra Madre Occidental, which is the largest volcanic province in the largest tertiary volcanic province in the world, with more than 350 different, large calderas that went off. We've got rhyolite plateaus that are over 2 kilometers thick in places, and there's a younger andesitic intermediate sequence beneath that, which is a lot tougher to map. Anyway, we're going to go into that in a little bit more detail. But so as I've stepped here to 40 million years, I guess maybe I can also talk about right now we are just having all of that andesitic magnetism. And I was talking about all those andesite flows and that we're cooking up this accreted oceanic crust. And so we're developing a really nice metallogenic province within this cordillera. And so now we've had just kind of steady subduction of the Farallon plate. And so I had a Paleo-Pacific plate. These plate names, there's a lot of moving parts here. Anyway, I know this is the Farallon plate that is subducting underneath North America. And we want to draw your attention to this lateral feature along the spreading ridge. And it's going to come in here kind of right around the border region. And I don't know if it's really there or maybe the border region created it because we had isostatic loading of all of the sediment and fill off of the Colorado Plateau. And so maybe the bottom of the craton was a little bit underplated there from an isostatic kind of rebound, and that acted to slice the plate or to cause it to break there better. But we've got a really good trend of metallogenic porphyry copper deposits. It's going to fall kind of just right underneath this plate. And so I'm going to step forward and we're going to start subducting this ridge. And as we start subducting this ridge, I'm going to jump into, so we just started subducting this ridge, and we've got some back arc extension that's kind of been going on for a while, but now it's going to get really accelerated. And we're also going to start having some fore arc extension, and along with this rib subduction and then the slab breakaway beneath, the tectonic environment is going to change very rapidly from this subduction setting to an extensional setting. And we're going to see Baja California take off like a race car and move like a Ferrari in geologic time. And I want to point out that, all of this extension throughout kind of the Cordillera of Mexico, I mentioned this high plateau of tertiary ignimbrites that are being emplaced right now, on this figure at 20 million years, kind of extending along the western margin of Mexico. We can see all of these big domes here, but that is these 350 calderas that even extends here into southern New Mexico and kind of right around the Arizona-New Mexico border. It just kind of gets broken here in this border region. Anyway, this is the time of the emplacement of these rhyolite flows. And so we can get relatively good age constraints off of these different flows. And there have been numerous studies, such as Murray in 2013, showing the timing of extension moving from the east to the west across Mexico. And so stepping forward to 15 million years ago, we see this back arc province really develops, and we've got the Chihuahua mobile belt in here, and it's extending, it's refocused all of this extension of the Chihuahua mobile belt, which is in this extended terrain. It's really focused right here along the Rio Grande Rift. And the Rio Grande Rift is maybe a story for another day, but we've got the Diablo Plateau, which is a little mini cratonic block sitting right in here. And that certainly probably helped vector all of that heat flow and concentrate it kind of into this corridor between the Diablo Plateau and the Colorado Plateau. Anyway, Lawton and McNulton certainly go into quite a bit more detail on Rio Grande Rift development, as does Randy Keller, as do a lot of other great scientists that I certainly encourage you to delve more into any of these subjects, because I'm just touching on so much. Here in the red, so in the orange, we've got this back arc extension. Here in the red, we've got the fore arc extension. And you can see we're still just kind of subducting our ridge. And I guess this big extension is more so related to there being a far lesser compressive component along the crust coming from the Pacific. I don't know. Maybe there's another scientist in the group that would want to tear me up for that. I'm not going to dive in anymore. Now, as we start pushing this ridge underneath the western side of North America, that's where we really start rip-roaring and creating and tearing the crust and creating this extensional province that is going to be the Gulf of California and transform on up into the San Andreas Fault, and then also, play a big component role. Well, we can't see the Basin and Range right here, but that's the Basin and Range of Nevada is a whole other story, another super extended terrain. I'm glad it's off of this figure because it would get me far too distracted. But as I said, a lot of these statements, they're based on the work of many, many different researchers. And Ferrari has done some great cumulative kind of studies down in Mexico, looking at entire regions and kind of putting together the local tectonics for, different, what are they, 100,000 K or 100,000 scale, geologic maps. And so large scale, but really detailed studies that I think, the combination of this large and small scale is just so important. But we've got really kind of detailed logging of the breakup and separation of Baja California from Puerto Vallarta, down here in the southwest of Mexico on the Pacific coast. So I gotta recommend Puerto Vallarta for anybody who hasn't been. That's the premier beach in Mexico. Fabulous jungle mountains right on the coast, and it's jungle, it's tropical, it's real jungle, real mountains, good stuff. Anyway, we see here at 5 million years. I mean, we're just at 10 million years and we're connected. 5 million years, we've already started opening the Gulf of California. Some detailed work by Umhofer out of Northern Arizona University, 2018, shows that we've got this there's good timing controls on this change from, it's a change from convergence to transverse, I guess. And so it's this transtensional stress that really initiates the rupture. And then once that rupture initiates, it really takes off. And I think I'm missing a slide here, but you guys get the point. We know what Southwest and North America looks like nowadays. Baja is all the way over here. It's a long way over there. It moved a whole lot in 5 million years. Our relative motion along that spreading, this newly developed spreading center is phenomenal. Anyway, we've got a whole lot of extended terrain. We've got a whole lot of terrain that was highly magnetized, accreted island arcs, accreted oceanic terrain, a ton of magnetism, and now we've just extended the heck out of everything as we subducted that ridge. And so, yes, let's talk about current day and just talk about kind of a couple of locations that I'm going to dial y'all into here shortly. But let's talk about the extension that happened. And, maybe it was certainly just talking about the extension in the basin and range and the different kind of extensional provinces of southwestern North America. Each one is its own talk in itself. But I think this figure just really kind of goes to show the crazy amount of extension that occurred. And so we have unextended terrain up here in the Colorado Plateau, which is just the northern portion of this picture. And so up here in the Colorado Plateau. And so everything else on this diagram from Nickerson Seedorf 2016 is extended by, 0.25% in the low areas and up to 2.7 times within kind of the basin and range super extensional trough corridor of Arizona, where we've got a bunch of metamorphic rocks exposed, and we've got these detachment fault systems and other mid to lower crustal structures. The transitions from brittle to ductile is exposed in numerous areas. We've certainly got a lot of rocks that are ductily deformed within different parts of Arizona, but we've got just the terrain that was just ripped right in half as well, kind of running right through here in the southern part of Arizona. And so we've exposed some lower crustal rocks. And now we're going to zoom in to this tiny little area of interest at Baghdad. And it's a tiny little area of interest, but it's a great big mining operation. But talking about the regional geology of Baghdad, we are in a metamorphic suite, and we're in the Yavapai province rocks. And these Yavapai province rocks, I was telling y'all and talking to y'all about island arc accretion. And as you recall, there were those little green blobs in the first figure I showed of the Proterozoic. And those island arcs and then similar oceanic intermediate style crust, which was accreted, generated some really prolific volcanogenic massive sulfide deposits, such as the Jerome deposit. I guess it's known as maybe the Verde copper mine now. And then there's another new discovery happened there at Iron Springs. But these VMS deposits, which are just volcanic, massive sulfide, kind of a black smoker style thing, or a late stage segregate from the right kind of magma and expulsive. But these are just massive sulfide bodies that, can be 5-10 meters wide and some of the highest ore grades on the planet. And so anyway, that's what mining at Baghdad started off as. And they were mining VMS deposits. They were mining VMS veins within the metamorphosed volcaniclastics. And these were located right around some quartz porphyry stocks. And as the price of copper and economics and everything else changed, mining switched over to these quartz monzonites. But the galena from the old Dick mine, for example, dates at 1.7 billion years old. And the nearby Lawler granite, which is just to the southwest, is a 1.4 billion year old kind of batholith that is within the 1.4 billion years old. It correlates great with the Madeira diorite that we're going to talk about here over at Miami Inspiration as well, or I guess that we're going to touch on. But I guess my point is that this is a prolific mining area, and I think it's quite coincidental that we've got multiple deposit styles, and that's certainly what we want to see in any kind of good mine. We want more than just one type of ore that we can put through the body, or, we need these multiple phases of enrichment, and certainly kind of we get a stacking effect where you've got different metals and elements that are mobile and available to a later mineralizing fluid and can be further transported and concentrated, or maybe act as a reducing agent and cause other mineralization to drop out and concentrate there. But I guess maybe the big point I just want to point out here at Baghdad is we've got this host rock sequence, which is itself part of a metallogenic terrain, and it is mineralized, and it's 1.5 billion years old. And then we got this, 75 million year old Laramide porphyry copper, which was later emplaced on very similar, probably structural corridors to, maybe similar structural corridors isn't the right thing to say, but the crust wants to break in the same places it broke before, and we want to have, deep seated, or the capacity for deep seated permeation of fluids, and deep seated fluid pathways and connectivity with the lower crust, and those are kind of the pathways that certainly have the potential to concentrate and influence the emplacement of magmatism. And then, it's not just magmatism, but then it's the later stage mineralized porphyry bodies that come off of it. And, multi-phase magmatism, but these long-lived kind of magmatic emplacements and posits, and then they're focused within some sort of intra-crustal corridor, which, could have been previously mineralized and is in this case. And we can see here in this figure from Anderson, 1955, the Baghdad porphyry copper deposit is just right here in the center, and then the quartz monzonite is this little intrusive next to it. But all of the other host rocks are Precambrian, and I guess we have a little capping basalt, and I know the basalt gets real heavy. This heloconglomerate and basalt flows, but the host rocks are kind of a nightmare to map, and so that's why they're not mapped here in detail. But also this diorite porphyry dikes, we saw it a few slides earlier, I guess, anyway. A lot of times the Precambrian basement, at least for me, on these postage stamps is nightmare to map. It depends how many controlling units you've got. When it's all nice, it's not very nice. Anyway, we've got these crisscrossing quartz monzonite porphyry dike swarms, and the X marks the spot. We've got the main quartz monzonite stock, and then the mineralized portion being there on the western front and going under the cover of the basalt. And it's the Baghdad mine in Arizona. There's certainly a whole lot more to say, but I think it's important to note that the Baghdad complex is hosted within a schist belt. And so looking at the Proterozoic rocks of central Arizona, we've got our schists and schisty rocks shown here in black. And we're talking about them being either felsic volcanics, mafic volcanics, or epiplastics, but we're talking about their metamorphic components now. And so the Jerome copper deposit I mentioned, which was one of the highest grade copper finds in the world, and propelled the Douglas Copper Mining Company to fame, and I believe that is now a big company in the world. I don't know. I'm getting out of my realm. Anyway, so the Jerome and Verde VMS deposits are right here along this schist belt. All right, and then we've got Iron Springs just down here that Arizona Metals Exploration or somebody is drilling out, and they've got a beautiful looking VMS. The Zonia deposit is down here. All right, and we're gonna pop them up here. Excuse me. Wonderful. All right. And so these are a couple of different kind of Proterozoic, or examples of Proterozoic mineralization that are here within Arizona that certainly have the potential. I believe Zonia probably does have some later porphyry mineralization associated with it as well. And then here, right southwest of Prescott, we have the Copper Basin porphyry. And this was one of the integral spots for Lowell and Gilbert in their studies and conceptualization of the porphyry copper model. Not because it was a great example of a productive porphyry copper deposit, because it was the roots of a porphyry copper deposit right there at Copper Basin. And so there's some productive breccious stocks that were kind of small scale in comparison to an entire deposit, but they had the roots of the system there. And there's also a little bleb of schist off to the side, and that schist, this schisty zone is very prospective for mineralization. I know of two projects right there, for example, that I'm quite familiar with. We're going to jump down here to Globe, and Globe is a very prolific mining province, and that's where the U.S. got the copper for World War I and II, or at least the vast majority of it. And we're going to talk about it, maybe the economics of a little bit more in the next slide, but now I just want to talk about the structure and location of Globe. In this map, Globe's not placed, but it's immediately under my cursor, immediately under my cursor right here. And so then we have some porphyry deposits outlined, and Globe's right here, some porphyry deposits outlined. But I want to note the extensive faulting and the extensive regional structure that we see on this map in the green and red and orange faults in this map from Mayer in 2088. And we're talking about extended terrains. And this is a heavily extended province. You know, it's extended like 2 times. And so looking at this idealized porphyry copper deposit model, this is from John 2010, and it's based on the Lowell and Gilbert porphyry copper deposit model. But I like the way that he displays it here, showing all the different mineral assemblages and the alteration kind of assemblages as well. And so this is an idealized system. And so imagine an idealized system and you extend it, you know, you cut it in half once, maybe you cut it in half twice. The guys at the University of Arizona in Tucson and the Lowell Institute, they've just been doing phenomenal work on these structural reconstructions across these basins. And so they take these things that are totally chopped up and they make these wonderful, idealized and regional stratigraphic sections and columns, and they are able to reconstruct and rotate back to original. And I think the exploration implications there are tremendous, and that's what Bronco Creek Exploration is doing, and EMX royalties bottom for that because it is tremendous. The implications are tremendous, but University of Arizona Tucson is putting out additional work like that regularly and up to this date, and Dr. Barton and Seedorf are some of the best, just top notch. Anyway, looking at a different figure, we can see all of the different porphyry bodies and then ore deposits as well here within the Miami Inspiration District, shown here by all of these red stars. This is the Old Dominion group over here. All of this is high up in the porphyry system. And so these are sedimentary rocks hosting the upper levels of porphyry style mineralization. And it's potential porphyry source at depth, 100% for sure. But as we get over here in the Miami, and Miami kind of, it's Miami, and then this is Inspiration, and that's Miami. I don't know, who knows the names of all these different pits. I'm sure somebody does, excuse me for saying that. Anyway, these giant pits are the actual kind of hearts of the porphyry intrusive emplacements, and then also the peripheral host rock material, because it was mineralized as well in kind of an exotic copper deposit style nature, and that's in the Pinal schist. But looking at this figure, just to get a scale for kind of how much copper is in this little neck of the woods with all these different red circles and stars, you got the old historic Cypress Amax Bluebird mine that produced 214 million pounds of copper. And then we have all of these other resources that are in place and kind of currently under production. Capstone mine, 1.4 billion tons, 0.3 copper. The Rio Tinto Resolution copper deposit is just right here, which is an intact porphyry copper system, and it's 1.5 billion tons at 1.5% copper. That's a tremendous, domestic copper resource that the U.S. needs to develop if we want to electrify and put everybody on electric cars and electrify the grid, and everybody wants a smart house and a smartphone and everything else. And we need more copper. And this is one of the places that I think it's going to come out of in the U.S., because this is a location that has the infrastructure. It's got the history, and it's been endowed with the metal. Looking at kind of what's left at the Miami Inspiration pits, there's the Miami East Leach, which has 266 million tons, 4.5% copper. Van Dyke deposit that's in place. They want to in situ mine it, 100 plus million tons at 0.3% copper. Miami Deep in place, 1.2 billion tons at 0.6% copper. Copper Cities, I believe BHP is just currently picking it back up and doing some drilling, or maybe somebody's just picking it up and talking about putting it back into production. 120 million tons at 0.4% copper. But a lot of times, these are also the published resources and published numbers that I've gotten. A lot of internal work is ongoing by some of the biggest mining companies in the world to advance and further develop and extend the time frame and viability of these deposits, because these are deposits of such size and significance that we're talking about 20, 50, 100-year life cycles on these mining operations. And sustainable mining certainly needs to be the way that we look at things going forward to the future. But this is in the copper triangle, and so I didn't rotate, but this figure is rotated with north facing to the west. And so Miami Inspiration is right here, and then the Ray Mine, the Ray Mine mining complex, and then the Asarco smelter and tailings facility associated down here by Florence and Hayden. This is an area that is incredibly endowed with copper, and it has the infrastructure to, take the United States through kind of the next 100, 200 years. And really, we really need to look at our mineral independence. We need to look at securing independence to our supply chain. And we are just so dependent on China for our raw commodities, whether they're, producing it there, whether they're controlling the place that's producing it, or whether they're the ones processing it and refining it. And that's the biggest thing. They got all the smelters and everything else there. And yeah, we don't want to build smelters here in the States because they're already ugly and dirty and stinky, but they need to be built. And somebody's going to build them. Somebody's going to operate them. So many topics to cover, but I don't want to get too sidetracked. Sometimes I like to run off. I have fun. I really enjoy my work, and I really love applying geology to trying to make a mountain into, I say mountain into a molehill, but I guess that's when we dig holes in it. So that's exactly it. I want to make mountains into molehills because we need to take these metals out of the ground, and I love doing field geology, and that's how I get to apply it. So anyway, please, I'm open to any questions.
Thank you, Mike. That was a terrific talk, and we have about 15 to 20 minutes for questions. So there are a bunch in the chat, I think.
I'm not seeing hands. I see that somebody asked if the the presentation slides were going to be made available.
No, unfortunately they're not. But if you shoot me an email, I'm happy to pass along some literature.
Yeah. One thing
yeah, and I got the chat opened up here, and so okay, I guess good. Anybody, if they want to ask questions, just put it here in the chat, and I guess we can just start. We just talked about copies of the presentation. We'll make the recording available after the fact. How do rare earths play into this? Well, there are certainly rare earth plays to be made, and I've focused my career as I specialized in gold exploration, in gold systems some wild earths are slightly different. And rare earths, one of the better places we get them in weird melts like cyanites and other stuff, and then flows associated to those weird melts. You can also have them in some pegmatites. I don't know so much about rare earths in pegmatites, but yeah, for sure in pegmatites. You also can get lithium in pegmatites. Lithium in pegmatites is good because it's just lithium carbonate. The lithium brines and lithium clays are an entirely different story when it comes to processing and mining. And you're also talking about a different scale of operations. I think that's something that any economic geologist really needs to consider with any project. Of course, you need to have a strategy in mind at the beginning of an exploration project, because otherwise you're just going to be spending money aimlessly. And so there has to be an end game at the start of the game. But I feel like a lot of projects are killed by scale, and so many, trying to advance projects as a prospector, and all these companies saying, we want 1 million ounces, or there's got to be 1 million ounces. And it'd be great if it was, but there's a lot of mines making a lot of money that barely have 100,000 ounces, and it's also a whole lot easier to permit an operation to only run through, 1 million tons of rock total, as opposed to 1 billion tons of rock total. Well, you're talking about the scale of everything's an order of magnitude. And so your permitting headaches are an order of magnitude, if not 2 or 3, because you're multiplying everything by an order of magnitude, And so I think we really need to see the domestic focus on small, high-grade production of metals that are strategic. We certainly need to be making our strategic metals as much as we can domestically where we can,
Yeah, Mike, the 2 rare earth deposits that I know of in the United States are both actually in extensional terrains. And in other countries, such as Brazil, rare earths are associated with carbonatite pipes, which I think are things that occur during the early stages of extension, during the sort of pre-rift uplift. But
I'm not exactly sure, but I got to point out Texas Rare Earth Resources there in Sierra Blanca they got a giant government grant from the Department of Defense for $30 million or something to go into production early. And supposedly their rare earth is like in fluorite rather than trapped in zircon or monazite, something else that's really refractory and really hard to get it out of. And so I'm really excited for those guys. And it would be great to see what happens there. And I don't want to say too much on that front.
Another thing that I noticed, Mike, is I was in the copper industry back 60 years ago and 50 years ago, and grades of porphyries then were above 1%. You wouldn't look at a porphyry if you couldn't get an average grade above 1%. And I see we're down at 0.3 and 0.4 now.
Well, yes, but at the same time, like a new porphyry down there in Chile, Ecuador, or the Andes, you're looking at those grades, but you're not in that location with the infrastructure and the ease to access and operate, and where you already have kind of the existing infrastructure to process,
Yeah, that's really important. Yeah. But you're also going to be shifting 3 times as much rock if you go to 0.3 grade from 1.0. And I think that's another significant fact.
I can't argue with that one bit, John. Yeah, grade is king. But at the same time, if you throw in 0.5 gram of gold, that's equal to 1% copper. And so that's why you always got to make sure about the gold credits and watch out for the gold, because in any type of metal mine, having that gold is very welcome to the economics.
Yeah. Andy, did you want to say something? No. But Mike, a question for you. Do you see any copper in Precambrian sedimentary deposits in this part of the world? You see any strata-bound copper deposits?
A little bit. I think. There is, a little bit of like VMS mineralization in some of the schist beds. Like, it's a component of the pre-metamorphic rock. But I think maybe the more important thing to point out, which maybe I didn't focus on and I just barely glanced upon. So there at Miami Inspiration, you had the Schultz granite, which is a big old granite stock. It's like 10, 15 square kilometers, right? And then you have 6 or maybe 8 different mineralized porphyry stocks that came up kind of around the periphery and at the end of that, magmatic event. And those are the mineralized bodies. But the margin, the Schultz granite came up into the Pinal schist. And that Pinal schist, where it is biotite rich, because the Pinal schist is kind of a turbidite sequence, or it had been a turbidite sequence. It was a continental margin precursor, and so you get biotite rich units and then more silicas, so dirty units, because it was a turbidite, right? And so the biotite rich units, well, they love soaking up fucking copper oxides. The silica rich formation, it maybe doesn't have the reducing component, or it's not texturally right for it. I don't know. But one of my slides showed the Copper Basin project for copper bullet mines. It's not Copper Basin, excuse me, Copper Springs. We've got the porphyry in place, and just immediately on the side of it, in the biotite rich Pinal schist, that's where you've got your disseminated oxide blanket with malachite and then chalcocite. And you've got a lot of supergene kind of primary, or excuse me, not supergene, but hypogene and primary porphyry mineralization alongside it in the porphyry. But half of that ore that they took out of the giant open pits, they went onto the leach pads in Miami Inspiration. Well, half of it was the Pinal schist. The other half of it was the porphyry intrusive, the stock. And so for that reason, it's incredibly important, because there at Baghdad, the schist is different. And the schist is not, hosting a kind of exotic copper deposit next to the porphyry deposit.
Okay. Yeah.
And so it doubles your fun a little bit over there at Miami Inspiration, because you've got the porphyry and then the rock off to the side of it that was enriched by the supergene processes that have acted upon this porphyry after you ripped everything in half.
Yeah. In my experience, some of these Precambrian biotite schists are quite carbon rich, so they have a reducing environment, especially early in their history, of course.
Yeah.
Anyway, Ted Smith.
Yes. Hey, there's a question here from Ted Smith. And man, this story over at Resolution Copper, those poor guys, they got such a phenomenal deposit. They put so much money in the ground. I can drive past and see that giant head shaft, and it looks phenomenal. And then you got these yuppie environmental jerks who didn't give 2 pisses about Oak Flats 10 years ago, but now, and nobody cared about it before that either. But now they're all up in arms, but they're going to drive over there in their electric car to have a rally and, hold on their cell phones for light and kumbaya or whatever. And I don't know. I like being out talking to the rocks and not thinking about that. and so they got a real headache on their hands. And, the administration, they're totally gridlocked for 2 years. That's the bottom line there. You got to wait for the administration to change.
What's the geology there, Mike?
The geology there is that you had the porphyry intrusive come up, and it emplaced alongside a large diabase, which would be like an andesite, an andesitic flow, so intermediate to mafic in nature. But as I might have said about andesites, they are kind of a nightmare to understand. And so, yeah, it's a diabase. But that diabase has a lot of available iron in it, just because of its nature of being an intermediate rock. and it just acts as a really good kind of reducing agent and host for mineralization. And so all of that mineralization that wanted to come out of that porphyry as it was cooling, it created just a glorious shell of mineralization into that diabase, which is where they've got that 1.5 billion tons at 1.5%. That's real. That's grades you were talking about, John. That's a real porphyry right there.
That's right. Yeah. Any more questions? Do you see any more? I don't. But no. So does anybody else have any questions for Mike? Because we have 1 minute left. If you do. Oh, there's a new message here. Hang on.
Yeah, I was just saying thanks, y'all. So I enjoyed giving the talk. Please feel free to reach out to me, anyone, if they've got further questions, and hope to see everyone soon at some sort of event out in person, because it's great that the world's trying to get back to this new normal that we're in. But get out there and talk to some rocks. That's all I can encourage everyone to do. Get out there and bang on some rocks. The harder you hit them with the hammer, the more they tell you. So there you go.
Thanks,
right.
Mike. We appreciate it.
Mike, when you're in Austin, come and get in touch with me. Okay.
Yeah, I definitely will, John.
Okay. And thanks very much. That was a great talk and a very swift overview of the mineralization. But what I really liked, though, was the campaign, the idea of these island arc belts being 10 times enriched in metal. So the more island arc belts you can pile in there, the better chance you've got of having a really rich mineral product.
Yeah. Well, I mean, you talk about, you've got your subduction related magmatism coming in, and it's underplating the crust and incorporating part of the crust. And if you're incorporating part of something that's enriched, well, the output's going to be more enriched too,
Yeah, and I guess the other important thing is these subduction-related magmas are pretty wet, so they're giving off a lot of volatiles that can transport the metals.
I forgot to mention that too. That has a big part to do with it. Yeah, that oceanic crust is wet when it's subducting, yeah, that really helps volatilize the lower crust, and that also, I feel like that's also probably playing a really big role in flat slab subduction versus steep, because when it's steep, you're subducting that wet crust real fast, and so you're melting and incorporating all that water into the melt. But when it's shallow slab subduction, you're like dehydrating and dewatering that crust before you melt it, and so it's just an entirely different event going on in the fucking mantle, and that's cool.
Yeah, and the other thing is the faster you subduct it and the quicker you melt it, the lower the temperature. The more water, and therefore the lower temperature, the lower the temperature of the melt. So I guess you get more melt for a given amount of subduction.
Yeah. Well, very neat stuff. I go off on tangents, but it's really cool how in the crust as well, you have such a different interaction, like in cold crust, from a granitic magma versus an intermediate or a mafic, just the way it's going to move, because it's got so much more temperature to work with. And then also kind of the differences in interaction with the wall rocks is kind of profound as well. You would think the hotter things would have more of an effect than they do, but like the cooler stuff, I guess maybe, yeah, it's wetter. It's all about the water. It's all about the water. If there's one thing magical in this universe.
Yeah. Okay. Any more questions for Mike? And if not, we can shut her down. And that was a great talk. Thank you very much, Wendy. Thank you very much, Kathy.
Thank you, John. Thank you, Mike.
Thanks, y'all.
And thanks, Mike.